Let g be the function given by g of x is equal to the integral from 0 to x of sine of t squared dt for x values between -1 and 3, including our endpoints. On which of the following intervals is g considered to be concave up? Well, we know that by the fundamental theorem of calculus part 1 that g prime of x will be equal to the derivative with respect to x of the integral from 0 to x of sine of t squared dt. And that fundamental theorem of calculus part 1 explains to us that the derivative and integral signs cancel each other out, and we are therefore left with g prime of x is equal to the sine of x squared. And now we have to determine where the function g is concave up. If you'll recall from analyzing functions with derivatives, concavity is found with the second derivative. So let's find the second derivative by taking the derivative of sine of x squared. So the derivative of sine is cosine. We still have x squared as our angle, but because our angle is more than just an x, we have to find the derivative of our angle, and the derivative of x squared is 2x. When you simplify it, the 2x comes in front. And now to determine the critical values of the second derivative, we need to set both of these pieces equal to 0. So 2x is equal to 0, so x would be 0. And then we would have, where is the cosine considered to be 0? Well, cosine is 0 at plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, and so on. So we're going to use these values to set x squared equal to each of them and solve. So we can have that x squared is equal to pi over 2. If we set it equal to negative pi over 2, we're going to get an imaginary solution there, so we don't even need that. If we square root both sides of this, we do need to include the plus or minus at this point so far. So let's evaluate the square root of pi over 2 in our calculator. So square root of pi divided by 2, and the pi divided by 2 are still in the radicand, so we can evaluate it, and it's calculating it correctly. And that ends up to the nearest thousandth being 1 and 253 thousandths. And now, if we think about it, here's our domain. We can't have negative 1 and 253 thousandths, so only the positive value is required for us. Now let's also set x squared equal to 3 pi over 2. Again, we're not setting it equal to the negative of it, because if we square root a negative, we will have an imaginary solution. So when we square root this, we have square root of 3 pi divided by 2. They're all within the radicand, so it's going to evaluate it correctly. So we have 2 and about 171 thousandths. So x is equal to 2 171 thousandths. If we do the negative, it's out of our domain, so we only want the positive solution here. Let's also try 5 pi over 2 and set x squared equal to 5 pi over 2. And when we do that and we square root both sides, x will be square root of 5 pi divided by 2. And that's all within our radicand, so we're fine there. If we press equals, we do get a value that's less than 3. So it is still within our domain. So we have 2 and 802 thousandths. All right. And again, the negative is not within our domain, so we can ignore it. All right, and just to make sure, let's try the square root of 7 pi over 2. Square root of 7 pi over 2. And if we evaluate that, that's totally outside of our domain, so we don't have to include it. All right, so now let's create our number line with -1 as one end. We had a critical value at 0. The next one was at square root of pi over 2, or 1 and 253 thousandths. The next one is at 2 and 171 thousandths, or the square root of 3 pi over 2. And then the next one is at 2 and 802 thousandths. And then we have 3 as our right endpoint. And now let's substitute values in between our critical values into our second derivative and determine the concavity behavior of our function. So between -1 and 0, let's try -1/2. So we're going to have 2 times -1/2 times the cosine, and -1/2 squared will be +1/4. So we can just put 1/4 in there and take the cosine of it. And when we evaluate this, we will get a negative value, meaning it's concave down at this point, or within this interval. And now between 0 and 1 and 253 thousandths, we could select a critical value of +1 here and substitute that in. So we'll have 2 times the cosine of 1 squared, or the cosine of 1. Let's evaluate that in our calculator. 2 times the cosine of 1, and we get a positive value. So we have a positive value here, meaning it's concave up. All right, now we got to pick a value in between 1 and 253 thousandths and 2 and 171 thousandths. We could select 2 as that value. So 2 times 2 is 4 times the cosine of 2 squared, which is also 4. So we're going to do 4 times the cosine of 4. And that's a negative value. So here we have concave down within this interval. Now let's pick a value between 2 and 171 thousandths and 2 and 802 thousandths. Let's say 2.5. Well, 2 times 2.5 is going to be 5. So we'll have 5 times the cosine of 2.5 squared. So 5 times the cosine of 2.5 squared. And when we evaluate that, we get a positive value. So we have concave up there. Okay, and now we have to pick another value between 2 and 802 thousandths and 3. So let's do 2 and 9/10. 2 times 2 and 9/10 will be 5 and 8/10. So we'll have 5 and 8/10 times the cosine of 2 and 9/10 squared, and close the parenthesis, and we get a negative value there. So we have concave down in between for this last interval. All right, and now we can answer the question, where is it concave up? Okay, it's concave up between 0 and 1 and 253 thousandths. It's also concave up between 2 and 171 thousandths and 2 and 802 thousandths. So that's Roman numeral 4. Roman numeral 5, that's concave down. Roman numeral 3 is concave down, and Roman numeral 1 is concave down. So we want Roman numerals 2 and 4, which are answer choice D.